Okay, thanks guys. I am from Altair, and I don't know if people don't think of Altair typically as a design company. I think we're thought of more of an analysis company and simulation. But we've been moving more into the design world, and I want to talk a little bit about our take on how we approach the design, really from a simulation standpoint. So just at a glance, Altair's been around for a long time, over 30 years now. Offices across the world. We went public last year, so we're a publicly held firm. Our mission and our vision statement really is to transform the way people do design. Our goal really is, since we come from a simulation world, is really to put simulation in the driver's seat for design. And I want to talk a little bit about how that works, and a little bit about how it's different from designing first and simulating second. So a little bit about our core business. We're probably best known for HyperWorks. HyperWorks is our suite of CAE tools, which have typically been in the hands of advanced simulation specialists for many, many years. We really got started in the automotive industry. We're in the aerospace industry. Altair is a company that really works at kind of the high-end specialized CAE where you have to solve really, really tough problems. And then we, a few years back, introduced our solid thinking lineup, which is a way to put that same great technology into the hands of designers and engineers who are not specialists in CAE. And then we have PBS Works, which is a high-performance computing management infrastructure. Carriots is the latest offering we have in IoT. And of course, the core of our business has always been engineering services. We started out as an engineering services company, and software came second. So when you think about the process of design, and this is kind of the mandatory big exotic 3D print video at the beginning of everybody's presentation here. When you think about design, it's changing a lot right now. There's additive manufacturing methods, there's topology optimization and generative design methods. There's a lot of new technology that's coming into play all at the same time. And that's creating this kind of confluence. There's another thing which is going on now, particularly in transportation, which is the electrification of automotive design. And that's driving a whole rethink of the way automobiles are designed. If you look at this, you're probably wondering, what is this thing that's being built right here? It really is, I don't know if you can guess, but you're going to see it at the end in kind of a reveal here. You can see it's brought together some topology optimization, it's brought together additive manufacturing techniques. There's a lot of handcrafting going on. It's one of these stretch projects. There's milling. There's a lot of things going together. This was a collaborative stretch project between a number of different companies, Altair, and AP Works, and CSI, and Heraeus. And you can see when it comes together here at the end, EOS was involved, and so forth. Altair gets involved in a number of these kind of advanced projects to really stretch what can be done. So that's really the integrated structure. It's a concept structure, the front end of a vehicle that incorporates crash criteria, ductwork. If you look at all the different disciplines that went into what that front structure is supposed to be doing, the idea was to bring as much functionality into a single structure as possible. So all of the cooling systems, fluid management, structures, etc., are all incorporated into this concept structure. So if you want a structure that's optimized for all of those things, that's a very multidisciplinary design project to do. We've seen a lot of examples today of topology optimization, where people just put some loads on something, get a topology out, and say, that's my finished design. That's never the finished design. Altair has been doing topology optimization since the mid-90s. We really introduced it to the entire world through the OptiStruct product. We've been engaged in practicing its use for 25 years. And you just see now in the last couple of years, the CAD systems are putting in, checking the box, and it's just very basic. Topology optimization is really not just about structures. It's about manufacturing considerations, and it's about all sorts of functions that go into the part. And you've got to get the load cases right. So Altair has been involved in a number of these kind of, I would say, iconic innovation landmarks over the years. People have probably recognized some of these. A lot of these are 3D print projects like the RUAG antenna and so forth. You see these things. Altair is always involved in these things one way or another, it seems. You've probably seen AP Works did their motorcycle project. I think everybody's got a motorcycle that's done an additive as well. We participated in that. But I'm going to kind of come down from the kind of these stretch projects and get a little bit more into the real world as we go forward and begin to introduce what it really means to do simulation and optimization-driven design, not just quick topology on parts. So here's a project with Amazzoni. This is a furrowing machine that goes out and basically plows up a field. It's a very big machine. They have this central structure that's part of the main apparatus right there in the center. And they had done a design project some time ago where they had, this was their conventional design for the structure. They had used optimization methods to come up with a lighter structure. Had a lot of performance improvements. They wanted to do a stretch project out of that one too and see if they could take it to the next step where they would use really a large additive manufacturing approach to build the casting. Casting is still a great way to make parts. We're all excited about additive manufacturing methods all the time, and it is exciting, no question about it, but casting is by far the more important in real-world manufacturing today. But additive has a place there too, and it's to help make the castings as well. So that was the approach they wanted to take here. Now that's a big casting if you're going to make it. So really a big part of the design project here is to see, can this thing be cast, and can it be cast efficiently in a time-effective manner, and can it be done without a lot of difficulty. So when you're designing a part, you're not just designing the topology. That was a given here. Yeah, we can come up with a good structure. We know how to go through load cases and do that. But what about optimizing it further for manufacturing feasibility? So here you're seeing a simulation of the casting process. And the cooling process, well, first you need to see if things are going to fill properly. Are you going to get cold shuts? Are you going to get areas that have air pockets, porosity issues, and so forth? Then you have to look at the cool down process as well. All of these factors can influence how you might want to design that part for manufacturability. So it's not just the basic topology optimization. It's really understanding the manufacturing process and designing for that as well. So just a couple other slides here on just the finishing of that part. So they actually did print out the blank for this to make the sand casting here, and it's gigantic 3D print sand machine here. See the process by which they make it. They pull the blank out of the sand, then they do the normal casting process. And they really made the part. It goes around on display, and I think they've used it. It was a concept part. The one that's in production is the middle one there, which is optimized. And if you look at the difference between the basic welded construction versus the one that they optimized, it's substantial reductions in weight, and performance has improved tremendously. And then they wanted to see if they could take it a step further with that cast part. And again, they got more weight reductions, thinner. It looks like there's more material, but there's actually less material. And they have quite a lot of reduction in the time to make that because of the casting optimization that was done on that as well. So let's talk a little bit about the process for simulation-driven design. And for us at Altair, you know, we talk about simulation-driven design, but that also means to us making design thinking influence the way you do simulation. It's really kind of a circular sort of a thing. They really have to influence each other in a loop. There's no real beginning or end to that process. So here's just a simple project that kind of illustrates, I think, what the entire process has to be. Again, we saw a number of examples of people running topology optimization, but in reality, you have a total design project, which is I have a certain function that I need out of the system that I'm building. Yeah, topology optimization has probably got to play in there somewhere, but I also have to do all the rest of the design. I have to size motors and springs and actuators and get the mechanicals correct. And can I use those mechanicals to actually drive the loads which are governing the structure? Because when you have to just estimate loads and put them on statically, you're going to make mistakes. You really want the mechanics, the dynamics of the behavior of this part to guide the topology optimization. That's very critical. And then you also want to be thinking about all the design iterations. The topology optimization results are never the final design, never. It's just the beginning of the design process. It really gives you ideas, it lets you explore, and then you have to do interpretations and realizations with other additional engineering knowledge that you have. So you have all these things you have to think about, even in a very simple structure. This is, by the way, a mechanism. It's a seat lever that would be under an automotive seat that lets you lean back, forward and backwards. Very simple structure. The design process in our software, this is the Inspire product, which has encapsulated basically a lot of our technology for designers and design engineers who are not finite element specialists. So one of the things you want to do in this project is design this lever, and you want to optimize it. So he wants to have the lightest lever he can, make sure it's stiff, but he also wants to make sure that the function of this whole system is what's driving that. So he's going to set this up as a mechanical assembly. So there's motions simulation built into Inspire as well. So here he's just taking the CAD, which is just dumb CAD, And it automatically detects all the locations where he has concentric holes and spindles and axles. It proposes joints for him. He can confirm the joints. And really just a few clicks, he can get the thing actuating. So he's just going to apply gravity to make sure he has a legitimate mechanism here. Puts a gravity load on. Okay, so that's working. So now we can actually put this thing through its paces. So put an actuator at the end of the lever, which is where some guy's hand is going to push it. First thing he wants to do is make sure he has a proper throw, he has a proper loads in the system. So he does a quick measurement. Am I getting enough throw? Maybe not. You probably have to do some geometry changes. So he's going to move some pivot points. There's some basic geometry editing tools in here to make sure that you can do direct modeling and move your pivot points around. Then he does a quick confirmation check, moves the lever, make sure his rotations are correct for what the mechanical assembly has to do. And now he's got to get the loads into the system, because right now he's just moving it kinematically. But there's going to be resistance springs and so forth in the system that return it to center. So he's going to put his springs in. In Inspire, we have all these mechanical elements like motors and actuators and springs and stuff. You just put them in, represents them in a kind of a WYSIWYG way, the way they really are in real life. He puts in an actuator just as a way to measure the force in that system. And again, just a few clicks, he can rerun the problem, and now he's going to have a fully statically determined system that has all of the resistance components in it, so springs and so forth. So now once you have that, you can actually then get all the loads you need when you move the lever and get the topology results. The old days you would have tried to think, well, okay, I think he's probably going to put so many forces in here, I'm going to come up with a couple load cases that represent it. What we really are doing here, we're going to run that through at every position that it can go through with the loads coming from the actual mechanism. So we know all the loads through the entire sweep of that part, and that is what becomes the boundary conditions. You don't have to guess at anything. So now he puts the actuator back in, and he can now run the mechanical assembly and just turn on Topology Optimization. Here he just hits run, and there's a number of different things you can ask for. We have a lot of manufacturing constraints, so if you know that you're going to be doing extrusions or castings or things like that, you can put those as constraints. So now he has the load paths. Again, the first results, those are never the final results. Now we use a method to capture these, which is called polyNURBS, and it's a manual process or semi-manual. We're getting it closer and closer to a one-click process. But there's a really high value to doing that step right there, which is that you get this control structure around the shape of that part. And you can do further optimization on that control structure. So we don't just look at that as a final design. You may want to do further optimization, just move all those controls and that lattice work that's around that. Here now he's run his part, he got his optimization. He just uses the same load case setup that comes from the mechanicals. And now he's going to realize that in different forms. So he makes 3 different forms of this lever. He's got one that's good for additive, maybe the one that's a sheet metal stamping, and then another one maybe that's a traditional casting, say. So we have feasibility checks in the software as well. So here I can do a quick feasibility check for casting. Just one click and it can tell me where I'm likely to get porosity issues because of typical cooling. Now I have a stamped version of the same part. I'm going to run a quick forming simulation. It can tell me where I'm likely to have thinning problems, where I'm likely to have high strains. And I might want to make quick design changes based on these really quick one-click feasibility checks. So for us, it's really important to be thinking about the manufacturing issues. You may decide, okay, that manufacturing process, maybe the forming is just leading down a path which is going to be a heavier structure. I don't like it. So you really want to be able to do these comparisons between these different realizations very quickly. Here we're working right now on an additive manufacturing setup. So you've seen it a million times, but we're putting it into our software as well, so you can design all your supports. It'll do suggested supports for you. You can do manual modifications. They're embedded into the system. Again, if you go back and do modifications to the original design based on optimization, the supports will carry along with it as well. And then finally, if you want to get more into the details of the casting or the forming, there's a whole series of really detailed simulations you can do for those manufacturing processes. Again, on the original part, same environment. So here we're going to set up casting. I'm just going to kind of skip through it. We have an entire way to set up everything there is to know about casting here. You can set up the mold, you can set up coolers and chillers and risers and runners of all types, and then just rerun the simulation in detail. So here we're looking at an example where, am I going to have cold shuts? Does the material begin to solidify before it closes off and reseals? that's a big deal. So you might want to go back, readjust your input conditions, just using the regular tools that are in here. For us, the goal is to put the optimizer around these so it can actually suggest areas to put in risers and things, so you don't even have to do that. If it knows you have a hot spot in the model and you need a riser, it'll suggest that and the riser volume to you as well. And so here he goes through just more and more details of setting up his casting simulation here. So what we've done then is created this Inspire environment, which started out as just basic topology optimization. It has motion in it. Now it has a manufacturing simulation for casting. We're working on forming, and molding is coming, and 3D printing and extrusion all in one nice form. And it's all about design generation. So we don't design a part and then just simulate it and see what we got out of it. You're really using the simulation to drive the entire design process in this product. Okay, let's look at another real-world example here. This is an injection molding mold. And if you're familiar with injection molding, it's a high-pressure process where you have a metal mold. You're usually going to make a plastic part, and you're going to inject molten, usually plastics or polymers, into these molds. They're actually quite high pressure. You have to push them together really hard because you don't want any flashing to occur. So the molds come together at pretty high pressure. And you want to use as little material as possible because you want to prevent the mold from heating up and staying hot, because that slows down the cooling of the part and it really reduces your part rate. So there's a lot of things to think about when you're doing the optimization for this. So you start with the design space here, and you could begin with the structural design of the die halves. So it'll come up with the minimal amount of material under the pressure you need to keep that mold in place when you put the polymers inside of it. That's step one. Then you also have to do the simulation of the cooling of this process as part of the overall job here. So you'll continue on, and you'll have to take into account the cooling, piping, the plumbing that goes through that, as well as the cooling effects of the surrounding structure you just designed. All of those have to work together to get the optimal solution. So we're putting CFD into it right now. We have all the CFD and cooling capabilities in the software inside of the HyperWorks products, and we want to put those into Inspire as well. So here's a case where the company that makes these injection dies, they make many of these things, uses this as their process today to design their dies. Their goals, of course, are really to get a low-cost die that's high-performing, but they really want to get their manufacturing rate to be very high. To do that, it has to cool very quickly. And actually, it says 25% faster production. After they went through this process with this die, they actually went from a 9-second part to a 3-second part, which is a really big deal in manufacturing. So, and again, it has to be a combination of cooling, so it's thermals plus topology optimization working together. And this is real. Okay, just looking at a couple other considerations on the manufacturing end. So here's one more example here I'll do with some of the optimization where there's two different realizations. This is some sort of lever handle that goes on a shaft. And there's a whole number of different things you have to consider with displacement constraints and so forth. So you set up the problem. The design space is that brick red color there. And you do a topology optimization. So on the left you have the original design. The middle one is your design space. You've opened up the space you want to use. And then you run your optimization subject to all those constraints and you get an answer. But interpretation is everything. So you could interpret it two ways, for instance, in this particular project, which was done. One is this very organic 3D printing type approach on the left. The one on the right is a more traditional sort of SolidWorks-y looking part that you could do. And you may have different reasons to interpret it that way, depending on your own design issues and other things that you're thinking about. And you might think, well, okay, that one on the left, it looks like it's 3D printing, it's all smooth, it's got to be the better part, right? That's what parts look like these days. But you really don't know the answer until you've gone through the whole thing. What's my manufacturing process? Which one is going to be more castable? Just doing a quick check, you'll actually find, it could be that the one on the left that looked really great, if you're going to cast it, it may take too long to cool down, so you're going to have to do more design iterations on it and so forth too. So knowing this upfront in the early concept stages is always critical. So what we've done is, because there's these design iterations that take place in the real world of design optimization, we put in these ranking tables so you can look at all the performance criteria of your parts and rank them against one another. Because anytime you're doing optimization, you're thinking about 4, 5, 6, who knows how many different disciplines that you have to judge these parts on before you know they're correct. And actually being able to visualize them and sort them in these built-in tables is very handy. So just kind of looking philosophically across things, you know, CAE, because Altair came really from that CAE world, it was used early on really to supplement test and then to replace some amount of test. Now we're seeing today, as we get into the 2000s, it's really becoming a significant driver in the design process itself, being used very upfront in these ways to actually get to the design upfront. So, which makes you kind of think, well, what about those guys who are the CAE specialists? So we're working kind of from that end too, because our customers, we have many that are high-end CAE specialists. We want to make their lives more design-like so that they can influence the design as well, even from the very high end. So we've gone back and we've been working on an initiative to, if you're familiar with HyperWorks, it's kind of had an older user interface. It has this new Inspire-like user interface now that's coming out. So it's much more of a design-oriented workflow in that software now too. So if you are a CAE guy, we're putting those same types of direct modeling tools into the CAE world. So you can do these direct modeling changes, lots of new morphing tools going in, and just grab things, drag them. What's cool is it's really sort of feature-oriented, even though it's a finite element model. We want the finite element guys to think about design changes in the same way that a designer would in a CAD system. So it's really identifying features inside of the FE representations of the models and letting you move it around just like you would in CAD. Okay, so Altair, as I said, has been practicing, you know, optimization for decades. And we know the pitfalls, and we've been applying it in really, really sophisticated way to full systems ever, not just little brackets and things. So here's an example of really how we begin to use it in full vehicle body structures. So if you look on the left, we have Inspire. That's really for this kind of generative concept design, quick, without thinking about finite elements. Those models can be promoted up into Hypermesh with the new user interface, and you can go into the full system level simulation and really detail it out with all kinds of additional details. But looking at automotive for a minute, it's a really great time in automotive for rethinking the car because of the electrification. You remove the powertrain, you remove the gas tank, you put in batteries. The whole vehicle structure is really being redesigned right now and rethought from the ground up, literally. We've been practicing for many years different ways to approach kind of an architectural process for doing this optimization for vehicle architectures, which we call it C123, but the basic steps here are, one is you do your load path generation using topology optimization. Now you can imagine the load cases that you would see on an automotive body. There's many, and many of them have to be linearized from like crash events and so forth for safety. So it's not just about putting a few loads on this thing, it's about really bringing in a whole set of boundary conditions that the real world car would see. And then once you've got the study of all these load paths through the vehicle, you also have, well, to set that problem up, you also have to create the design space as well. So there's a lot of things that go into the design space generation for a vehicle, including where the doors are and the seats and people. There's lots of negative spaces and positive spaces, which create a very blocky sort of design space that then generates those load paths. Once you have those load paths, those get interpreted. So you're not done there. That's not a finished car by any means. It's just a blocky set of load paths. You then refine those load paths into what a car would actually be, which is sheet metal that's been stamped and cast in different areas for joints and so forth. So then you begin to interpret those designs into these sheet metal structures. And again, you want to stay low fidelity at this point. There's no one-button car. So you have the low fidelity beams that come out and the joints, and you do some optimization on those. You optimize cross sections, you look at lots of iterations, and so forth. And so you go through this continual refinement, and the vehicle gets more and more accurate towards, from a very blocky thing to a final sheet metal part. And there's no CAD in the loop here. There's not one bit of CAD that's been brought in other than maybe some historical data. You're really working totally in a simulation environment, an optimization environment to do this. This is the way it's being done today. This is not, you know, far in the future. This is the practice today that Altair has developed and is using with its customer base. That's what it looks like to set it up in these problems. Another thing to think about with optimization, and this would apply not just to vehicles, but optimization in general. But vehicles are a great case of it. Here we have multiple configurations of this vehicle. So it has, say, the sedan. It's got maybe a wagon version. You have different roof configurations. There's multiple configurations of these vehicles. And there's a lot of carryover pieces. Maybe the bottom structures, you want a lot of carryover there. You want the optimizer to give you the same answer for the bottom structures because you want those to be carryover, but you still have to optimize it for not just one vehicle, but all the configurations. So the optimizer is really optimizing all these models simultaneously. When you've told it, please give me carryover parts. And that's something else that you don't do when you're just doing brackets, right? This is systems level stuff. Lots to think about. So here, in a typical automotive thing, you'll have the bottoms are all the same for all these configurations, and you'll have unique tops. So that gives you your optimization across all the vehicle configurations. And then you can think of new ways to realize it. And this is some area of research that's going on today, which is what's the fastest way to realize these load paths through the vehicles, not just as these kind of organic shapes, but as something that would be close to manufacturable. So here you have, we're fitting over the topology results, fitted beams. We know what the general shape of the beam section has to be so we can fit those to those rails and things. So you get nearly finished sheet metal for your beam structures when you realize these things. And then once you have these, you'll then do further fine-tuning of the optimization of the cross sections and so forth. So what I really want to leave you with this particular illustration is just the levels of steps you go through in a really holistic optimization process. It's not a one-button job. There's a lot to be thinking about, and the software needs to support these types of processes. So this is just kind of a summary slide of that whole architectural approach to optimization. Again, it's done with vehicles here, but it really applies to any kind of structure. It could apply to buildings, it could apply to ships and aircraft and so forth, where you're really dealing with multiple configurations of the product in multiple stages of fidelity, from the topology optimization to the beam structures and then the joint structures and so forth, all happening simultaneously. Okay, and then I'm just going to leave you with one last example in the medical field, which is another great example of optimization where you're not necessarily looking for the best lightest part. You're looking for something that performs in a very specific way. In the medical field, when you put an implant in, here's a femur implant that we're looking at here, there's a particular challenge which is unique. You don't want the stiffest part. What you want is a part which matches the stiffness of your own bones. If you have, you know the way bones are, right? If you stress a bone, it grows more in that area and becomes stiffer. If it's unstressed in an area, it becomes weaker in those areas. So the implants, if they create artificial stresses in local parts of the bones, they can grow too much in certain areas. If they don't stress them enough, they get too weak, and then you have failures. So what you need to do is design an implant which behaves as much like the actual bone does in terms of its stiffness and compliance as the original bone did. So your optimization goal is stiffness targets to match the bone. And you set goals to minimize the difference in stress that the bone would see if there was no plant in it. So here's maybe a healthy femur that's been subjected to the typical load cases, and there's quite a few load cases on the human femur that you have to account for. If you put in a traditional implant, you may create lower stresses on some areas and think that's good, but it's not, it's bad. You actually want to stress those areas properly. So what you're really doing is targeting these same exact stresses so that you get a part like this. So here we're using some lattice optimization to get just the right compliance in all the localized areas of that implant right there. So just another example of setting up the objectives and understanding what you're really trying to design with these is very important. So that's it. I just wanted to bring some of those examples to the floor because we see a lot about topology optimization, but I always want to leave people with the understanding that there's a lot of science behind doing it, and you have to be very cautious and really think about your engineering problem when you're doing it. So, thank you.